So thank you everybody for spending your lunchtime with us. My name is Vipul Bhushan. I'm one of the people with the MIT CIO Symposium, bringing you this great full day of content, and thank you for joining us on a nice spring day. In my professional life, I do risk and analytics in the investments division of a Boston area financial service company, but I like to get away and come back to the Institute and help put these together, and it's gratifying to see so many people here. So today we're going to hear from Joe Biron from another local company, PTC. He's going to talk to us about capitalizing on digital transformation, and Joe is the Chief Technology Officer of the Internet of Things segment at PTC. We'll go till about 12:50 or so, let him show and tell, and then after that do questions and answers for 15-20 minutes to give people enough time to get to their next thing. It starts at 1:15. Thanks very much again for coming.
All right, thanks, Vipul. So how's everyone doing today? How's the summit, the symposium going for everybody? Good? Looks like a really good lunch. I can't wait to eat mine. We'll get there soon enough. It slows me down right before I present, though. So as Vipul mentioned, I'm the CTO of IoT at PTC. How many of you know who PTC is? Oh, awesome. That's fantastic. Well, for those of you who don't, this is not a sales pitch, but just to give you a sense of where we're coming from with our perspective, PTC began its life in the 80s as one of the first, if not the first, 3D CAD programs. So PTC stood for, kind of like KFC, it doesn't really stand for that anymore, stood for Parametric Technology Corporation, because we pioneered parametric CAD design, whereas you were creating one part of your design, it was parameterized so that the rest of your design could morph and change. And so that put us on a journey of serving product manufacturers. And really now we look after the entire life cycle of product management, product manufacturing, from the engineering, the design with CAD programs, the project management, the bill of materials management with a category of software called product lifecycle management. We invested in IoT starting about 5 years ago, and so now we help look after the service and operational efficiency of the products once they're put into their active lives. And with augmented reality investment we started 2 or 3 years ago, we help the operation, help the people use the products and the machines. Part of this is about automation, and part of this is about giving the people who are using this industrial machinery superpowers. So that's our mission in life. Today I want to talk about this fancy buzzword, and I really hate these buzzwords, but I'll explain this one. Have you seen this buzzword recently, digital? Right. So what I hope to do over the next 32, 33 minutes is demystify this term and how we apply it towards what we call industrial IoT, but also beyond IoT, how we're helping industry, specifically product manufacturers, how we're helping them digitally transform their business and how that manifests around their enterprise. So from the engineering department to the service department to the manufacturing floor and sales and marketing and back again. So this is a pretty big deal. By the way, I've been doing IoT since 2007, before it was called IoT, helping product manufacturers connect their machines to the capital I internet so that they can monitor and remotely service, et cetera. And I've seen, not referring to this specific slide, but when IoT started to really become a thing that people were talking about, we saw lots of big numbers. They're going to be 1 billion connected things by 2020. And then somebody else said, no, wait, it's going to be 50 billion. It was almost like a one-upmanship for how big you could get the number, and it didn't matter how you justified it. So putting that in perspective, here's another big number. IDC, a very well-respected analyst firm, has quite a bit of research behind this number. $1 trillion unlocked through so-called digital transformation, and 30% of that in discrete and process manufacturing. So for those of you who, by the way, I asked how many of you knew who PTC was. How many of you are what you would call a manufacturing professional? Okay, so for the rest of the room, and I didn't know a lot of this stuff 5 or 6 years ago before I joined PTC. Discrete manufacturing is when we're producing something. So the output is a machine, a device, a widget, something that's a discrete good. And process manufacturing is what we refer to when it's food and beverage. So if you're making cornflakes or beer or oil or gas, refinement or petrochemicals or to some extent pharmaceuticals, the output isn't necessarily a discrete good that you put in a shrink wrap and put it on a shelf. It's a raw product transformed into a finished product. So we'll talk a little bit about those differences and how the technologies that have been the advancements in the last 10 years are being applied to those industries in manufacturing and, again, the whole life cycle of development, product development. So here's a chart I came up with a few years ago. I found myself, actually, right on this campus is a new nanotechnology building. And a couple of years ago, I was touring the building as it was in its construction state. And I found myself up on the roof with the engineers, and we were looking at the controllers for the HVAC system and the electrical panels and so forth. We were talking about how to instrument those in a smart way for building management, et cetera. I had a hard hat on, and I had to climb ladders, and it was dusty. And I thought that was really cool. And it made me reflect in that moment. I went to school for computer science, did the whole, I'm going to build video games for a living. No, I'm not going to do that. I'm going to do, so I studied all the AI and all that stuff, and I love computer science. I love software. But I reflected, what am I doing here? I think it's cool, but there's some intersection here that happened, and I didn't stop to contemplate it before. So I came up with this thought. I call it Biron's Law. So see what you think about this. As advancements in technology have happened across human history, certain advancements endure. Electric light, electricity, alternating current, to be more specific. Imagine in the 1839 Chicago World's Fair. I have the year a little bit off there, but when Tesla showed the world what alternating current technology could do and lit up thousands of light bulbs at the Chicago World's Fair, that was super cool. Holy crap, I can't believe we can do that technology. Does anyone think that about alternating current today? No, so that is, as these technologies endure over time, some of them peel off and we forget about them. The ones that endure become part of the fabric of our lives and are table stakes, and also at the same time become absolutely critical infrastructure for modern life. And we forget about them, they're not cool anymore. What we're doing with digital transformation is we're intersecting the hottest, coolest new trends in technology, and we're looking for what's this intersection where the critical technologies that run the planet, what can we do with the modern technologies to make those critical systems more well-behaved, more operationally efficient, more resilient, more reliable, et cetera. And this is one of the ways that we do recruiting at PTC. When we recruit top talent from this institution, other Massachusetts institutions, and around the world, we help young technologists understand how they can best put their creative, innovative ideas towards not just the next messaging app, right? The world does not need, I'll go on record and say, we don't need another way to send a text message to each other. Just like stop doing that. Let's work on this problem. Let's change the world with that same cool technology. So for the real math geeks in the room, by the way, if you want to complete my set theory, we're looking for the set of use cases where X is a member of the cross product of the intersection of cool and critical. That works really well with engineers in the room. Maybe some of you are probably engineers, maybe most of you. Okay, so the cool technologies that we're looking at applying, and by the way, we're not starting from the perspective of how do we apply this cool stuff. We're starting with the challenges that we know, and I'll get into that, from our customers. But some trends, high performance computing and cloud computing, for sure. We all know that. AI and generative design, and I'm going to explain in just a little while what generative design is. It's a subset of artificial intelligence. Additive manufacturing, this is 3D printing, some amazing things we can do now with 3D printing, and it's going to revolutionize the way we do parts management, the way we design parts for machinery. Whole new world here, and I've got a cool video I'll share with you to show what that really looks like. And industrial IoT. So importantly, we qualify IoT with industrial. Because I have a Nest thermostats at home, I have a SmartThings hub and smart switches and light bulbs, and all that stuff is really cool, but that's consumer IoT. I'm happy with that in part of my life. Industrial IoT is focusing on those mission critical systems that run the planet. Not that my home shouldn't participate in that, but what's different about it is the level of criticality and the enterprise grade that our solutions need to have. Stop for a lot of drinks of water. There's a lot of pollen in the air in my house today. Okay, so we look at the challenges that our customers have. They're predominantly product manufacturers or process manufacturers. And if we just go around this racetrack that depicts their enterprise, the first stop is the engineering department. And so the disruption that's happening in product engineering is generative design. What are the new technologies and tools that I can use when I'm designing my physical products? And what are the disruptions in the manufacturing process, such as additive manufacturing? Just an explanation of that term again. 3D printing lays down a substrate and builds up something layer by layer. That's why we call it additive manufacturing. We're adding stuff to produce a part. Most manufacturing is subtractive. We start with a block of steel or a block of wood and we whittle it down until we get some steel and we bend it and shape it. And so that's subtractive. That's the common manufacturing that we've had historically. So we look at how does the disruption of additive manufacturing tie back to the engineering challenges? How do you design stuff that will be additively manufactured? You definitely need a new technique and a new way of thinking about things. In sales and marketing, for some types of products, it's difficult to take an earth-moving machine into the showroom. And so how can we give customers the experience of understanding what they're going to buy or lease without having to have the physical good there? So there's some disruption in that sales and marketing aspect. And you'll see when I share some survey results, manufacturing and the supply chain, optimizing how products are built, the literal manufacturing process, but also all the peripheral activities around the manufacturing process, getting raw goods on time, getting the workforce scheduled, and so forth. Customer operations intersects manufacturing. Some of our customers' products are complex machines that are then put to use in industrial activities like wastewater treatment or smart city gas movement and so forth. So it may not be necessarily a manufacturing operation, but it is in fact an industrial operation. So how can we help make those machines that are used in those processes work better and work more synergistically with the other systems that are commonly found? And really, in my personal opinion, as an IoT practitioner for 2007 to 12 years, the first killer use case for IoT was customer service. So for product manufacturers that have, again, a complex asset and very likely a service contract with their customers, I'm going to fix your stuff when it breaks. So when you call me and say that it's broken, I have to put a dude in a van who rolls out to your site, physically diagnoses, finds out I need a part, goes back and gets the part, et cetera, et cetera. So by connecting the devices, we're able to troubleshoot remotely. We're able to interact and diagnose, sometimes even remediate the problem if it's a digital problem. It needs a new calibration profile, it needs a firmware update, et cetera. So service optimization has been the killer use case for IoT for a long time. The trend is changing. We're starting to see some balance. And then the corporate CXOs, whatever. So I want to share for a couple minutes. Time goes fast when you're up in front of people. We did a survey. We do an annual survey for our customer base, our partners, and our field operations folks. What are people most buzzing about where are the use cases landing, what's resonating. So this is really interesting. Where can you see, this is specifically about IoT. So how can connectivity help your product development exercise? A little bit. People really aren't sure. We have some ideas at PTC about how sensor data from products in the field can influence the design decisions being made in the engineering department, but that idea still has yet to catch on, really. Manufacturing has just jumped off the chart. There's a couple of reasons for that. For a long time, particularly in process manufacturing, for those of you who understand manufacturing, a digital controller that controls the machinery, also known as a PLC, a programmable logic controller, that revolutionized the so-called third industrial revolution. It was automation. Can I make this work cell that's producing this widget? Can I automate the machinery so I don't need a person pulling a crank or moving something from one side of the work table to another? So PLCs are the engines that power that automation. And it turns out those PLCs have the ability to liberate a lot more of the information they can collect for the purposes of integrating with the rest of the operation. So as we've turned on to this idea, using the connectivity already built into those automation systems to optimize the manufacturing process, manufacturing has become a very, very top use case for IoT. I mentioned service, the killer use case remains to be a killer use case. In operations outside of the manufacturing floor, we're starting to see how those same technologies can be applied to wastewater management, petrochemicals, et cetera. And because it's industrial IoT, the end customer typically doesn't participate directly, but they obviously get an indirect benefit. So we can keep on track. So yet another way to think about where we focus our efforts, where manufacturers in general should focus their efforts. We think about the products themselves. So products that drive what manufacturers want to do is design products that are differentiated from their competition and just work better, more innovative. And how can we do that with connectivity, augmented reality, and AI? The processes that create those products or the processes in which those products show up in, the killer app is efficiency, operational efficiency, make my operation more reliable, more resilient. And then, by the way, there are still people part of those processes. And those people need skills. And there happens to be a problem in the world with worker shortage. Baby boomers are retiring, and the kids in school haven't seen my Biron's law chart. So they may not have the idea that there could be a fulfilling, creative, innovative career in industrial. So we're trying to help change that. So let's show a couple of things on, this is going to be, all right, so this is a view of a CAD model. This is PTC's Creo product. It's a CAD design product. So let's say we're designing this part. Pause for a second. Our objective is to understand how the stresses that this part will undergo during its use, how that could potentially cause microfractures or failure of the part. Okay, so these colors are showing visually for the designer, and based on calculations like computational fluid dynamics and finite element analysis and all kinds of fancy math, here's how this part you just designed is going to experience those stresses in the real world. A couple of years ago, this was an overnight calculation, and the engineer who designed this piece of the model would look at a bunch of numbers the next day to understand where the stresses were. Because of GPUs and Moore's law, we're able now to take those same computations and execute them in near real time while you're physically designing the part in a CAD program like Creo. By the way, how many of you know about GPUs and where they can be used outside of video games? So here's really kind of the dawn of recognition for me a while ago, because I'm a computer science guy, so I maybe knew some of this stuff before most technologists, but GPUs are really good at matrix multiplication. I've got two matrices of numbers and I want to smash them together and compute some result. In computer graphics, you do a lot of that. Creating triangles and interactions, and do I need to show this part of the screen right now? All this matrix multiplication is happening all the time, and that's what GPUs, graphic programming units, were designed for. It turns out that computational fluid dynamics and finite element analysis also uses matrix multiplication. So GPUs show up in these advancements. It also turns out, I'll just click to my next slide here. When we talk about generative, machine learning and AI in general also takes advantage of matrix multiplication. So if you're NVIDIA, life's been really good for the last few years as we've unlocked all these use cases for the same GPU technology. So here's our same part, but this time, instead of manually designing and seeing in real time what the stresses are going to be, we're going to tell the program the constraints. Here's the box that you can fit inside. Well, I want to optimize for strength and lightness. This is AI at work, giving the engineer several design options automatically generated, given the constraints that the engineer supplied. Here are some options for you. And so we end up with parts that look a lot different than if a human being designed them. Pretty interesting stuff. Just like a bird bone has this weird lattice kind of structure, people would never sit there and design a bird bone. But an AI algorithm can and might come up with such designs. So we're finding these places. No one's going to completely design a snowmobile purely with AI. But these incremental steps actually add up to quite a big transformation. Okay, so that was the engineering part of the house. Now we talk about my favorite killer use case for industrial IoT, and that is service and support. So you probably know these kinds of pieces of equipment. Who are the people that typically fix Caterpillar machines? Is it a homeowner? No. Is it Caterpillar? Usually not. It's actually the dealers and distributors. So Caterpillar needed a way to give their dealers and distributors a tool that let them manage their business and their service for their region or subset of the market. So they're using IoT. They instrumented their machinery across many different product lines, generators, backhoes, and so forth, instrumented the machinery with communication modules and sensors that they may not have had previously, although a lot of that stuff is already built in. Most of you drive an automobile, I'm sure. There's something in your automobile called the onboard diagnostics port. It's right by your left knee when you're driving. It's where you get plugged into when you get your inspection sticker. In heavy equipment, there's a similar technology. It's called the J1939 standard. And a lot of the engine stuff is constantly blasting through that. And so by tapping into that stream, a lot of times in industrial, by the way, we find that the data was already available somewhere. We just needed to liberate it and connect it somewhere. And that was really the way that Caterpillar has done this. A little bit different, our technology is in a lot of ATM machines. So Diebold is a major manufacturer of ATM machines. If you've used an ATM machine in the last couple of months, you probably used a machine that had PTC technology inside of it. And for the most part, an ATM is a computer, not surprisingly, but it also has a cash receiver, has a bill dispenser, has all this electromechanical stuff. And so Diebold needed to manage their service cost. We can't have truck rolls every time we need to diagnose an ATM machine. So if you've ever seen an ATM machine that said this machine is currently not in service, there's another video screen that you can't see that a remote service engineer is using that is helping them troubleshoot and diagnose the machine, potentially send a software update. And importantly, if there is a part that needs to be replaced, they know what part they need to replace, and they show up on site with the right part in hand. A lot of times these are pretty simple use cases to understand, but the overall benefit really aggregates. A little bit different, this is Sysmex makes blood analyzers. So it turns out when you're analyzing blood, the chemical reactions that are part of the analysis require a reagent. So these things here that look like printer ink cartridges, they look exactly like printer ink cartridges, don't they? They're reagents, and you can buy those from other suppliers, but Sysmex really wants their customers to buy their reagents from Sysmex. And so, well, what if while we're doing that service stuff and making sure their machines are staying online, why don't we also give them an automatic replenishment schedule, not based on some baloney time frame that we probably don't really know, but we're monitoring the levels of the reagents and we're going to proactively ship simple stuff, but an example of a business model, automated consumable replenishment, that really just doesn't work unless you can connect to it. Anybody want to guess what this thing is? Come on, you've all seen these, right? Okay, this is a reciprocating hydraulic engine. Colfax is actually a conglomerate with a couple of different divisions. This division's Howden. They make industrial blowers, big air movers, and something like this would be used in gas and oil refineries or petrochemical facilities or wastewater treatment. So I'm moving lots of gas or liquid from one place to another. Giant things with giant parts and giant problems when things go wrong. So it's more of the same. It's how do we proactively monitor and understand what's going to happen before it happens. By the way, knowing what's going to happen before it happens, it's called prediction, right? There's a lot of talk and good implementations of AI for predictions, specifically the subcategory of AI called machine learning. So here's how there's one slide I really want to talk this over. Okay, we'll talk it over this one. So yet another use case, train, air conditioning units is probably one on the top of this building. Same story, same idea. Let's optimize our parts. So PTC has another product beyond IoT and CAD we call service parts management. So what SPM is all about is trying to predict where the parts should be and which depots, if you've got a global operation, where we're going to need these kinds of parts, and let's balance our inventory so when a repair tech needs, I don't know, an evaporator coil for this AC unit, they have a regional distribution center that they can find that part. It's actually a big problem to solve. Historically, we've done this by just having fancy algorithms that looked at historical parts requirements, but we knew nothing about actual machines. Now, with IoT, we can know how those machines are behaving. Things like cycle counts, how often does the condenser come on and off, those can be somewhat of a prediction, but that's an example of what I'll call a heuristic. A heuristic means it's a rule of thumb. The engineering team maybe had some tolerances or recommended cycle counts before replacement. Remember when we used to be asked to change our engine oil every 3 months? That's a heuristic. Do they know how dirty my engine oil was? No, they don't know how dirty it is. There's no sensor that's seeing how dirty it is. They just said, hey, Joe, probably do it every 3 months, 3,000 miles, you'll be good. These days, that doesn't happen, right? You get an indicator, your car says, hey, Joe, it's time to change the oil. It's been 11,000 miles. Well, part of that is because the manufacturer started doing bumper-to-bumper warranties with oil changes built in. But another part of it is just this idea of using historical data to understand what the real usage should translate into proactive maintenance. But then there's only so far we can go with things that a human can code, right? If the engineering team or the service teams know if this, then that, great, they should code that. Might be a simple rule, might be a short calculation, no problem. Where AI really helps, and specifically machine learning in these cases, is when there is no human that knows the confluence of events, the history of how this thing's been used, and the environmental conditions, and the training level of the last service person who touched it. All of these things go into some weird cocktail that a machine, if it had access to the data, could make some predictions. That's what machine learning does. It eats a lot of data. It learns from the data. It doesn't really learn about the problem. It just puts weights, numerical weights, and I've seen this before. When this happens, this happens. And it sets up all these weights, and with enough data, you can have some predictions that are meaningful enough to act upon. And that's the revolution that we've seen with the so-called predictive maintenance and proactive maintenance. The application of heuristic rules, simple calculations, maybe complex calculations in the form of simulation and FAEs and CFDs like I talked about before, and machine learning for those use cases where no human being knows what the formula is, so we need machines to help us figure it out. Any questions, by the way? We can break for questions in the middle. Great.
For that large pump for the oil and gas or hydraulic, so maybe there's 10,000 valves and gears and whatnot. And so when I get the sensors and the machine learning, it can say that the pressure is off, but how will it tell me, unless you have sensors on each valve or distill it, how do they know where, how does it triangulate into the actual thing that needs to be replaced because it's so many moving pieces?
Yeah, that's a great question. So sometimes the engineering teams know, based on their simulations that they do in the design process, and similar to the visual we saw with the stresses on that part, the engineering team may know when this happens and this happens and these things are lined up this way, it's going to cause some downstream effect. That's what we'll call a physics-based model. We know from first principles, physics and statistical manipulations and simulations, that this will probably happen. And then when they don't know those things, and when we don't know what the inputs and the outputs will be at all, this is where machine learning can help, because again, it can't be stressed enough. Artificial intelligence does not understand anything. It knows nothing, really knows nothing. They're fancy techniques for manipulating numbers, and the net effect can be, wow, it told me that. It told you that, but it didn't. The machine doesn't know what it's telling you. But it's using a technique that humans are applying to these use cases where some surprising outcomes can, one example we had was, and I talked about this a little bit just now, we had a customer collecting lots of samples of the automation status, the sensor values, et cetera, and the machine learning wasn't making matches. It couldn't really correlate an outcome until we added the HR training records. And then we started to see tight correlation between certain combinations of events and the number of training hours the technician had. It's the stuff you could never imagine being the cause. It will find that cause, again, not because it knows how the dynamics work, but just because it's a machine chewing through numbers in a way humans could never do. History is important. Yeah.
How far down and how long is it going to be before you can move some of the diagnostics into the consumer, into the home for the appliances, and monitoring what's going on with the appliance to come up with a diagnosis that then tells the repairman what part he needs to break. Right now, as it works, microwave was damaged by lightning. They had to come out first, check out what needed, other parts,
Yep.
and then they had to go back, get the parts ordered up, and bring them up. So when will you get to the household with diagnostics so that the repairman knows what to bring the first time it comes out?
Oh, I'm with you there, because as a homeowner who maintains my own stuff, and I see all this stuff happening in industry, I'm like, why can't my HVAC guy know? I think it's gonna, my opinion is it's gonna just come downstream. It's gonna come down market. As we're working out the kinks, we know how to do this for industrial use cases. We know how to do this for buildings, et cetera. When the costs are coming down, the expertise in deploying these kinds of solutions is gaining traction. It will come to our homes soon, I believe. More question before I continue?
Well, thank you for the presentation. I think
I'm not done about it.
we're very vocal about for many people in manufacturing, and it's obvious that there is a lot of value can be created through analytics. How do you address the concerns of manufacturing managers asking you, is it really safe to connect to the cloud?
Yeah, so good question. Let me skip forward a little bit and answer that question over a couple of slides. By the way, real quickly on this, the classic manufacturing information technology stack was like this. PLCs are controlling equipment. We've got human-machine interfaces that show the operators what the machines are doing. We've got a manufacturing execution system that's smashing together our work orders and scheduling the work at the cells. And we've got some overarching business systems like ERP that are telling us about our orders. So with all that in place, which is the status quo, people don't know what the hell's going on. Because The operators get one view, the people in the back office get another view, and that really needs to be integrated. So the digital transformation opportunity here is to apply newer advanced technologies like IoT and augmented reality and AI to insert in the middle to rapid extend those existing systems and bring the information that the right people need at the right time, automate decisions, et cetera. Along the way, this is where I start to answer your question, along the way, we've connected stuff that wasn't meant to be connected when it was originally designed. And so how do we make that safe? Well, for one thing, if a PLC, and by the way, a PLC in your mind, imagine just a box with some leads that get electrical signals on one side and put electrical outputs on another. And you program it to say when that line and that line and that line are energized, I want to energize this other line. And with that simple device, this is a super simplification, of course, of what a PLC does. With that simple device, I can make things actuate. I can make machinery turn valves. I can open up solenoid, energized solenoids that make all kinds of very powerful things happen. And there are safety critical controls in such PLCs to make sure someone doesn't get their hand chopped off. You don't want that stuff getting executed in the cloud. So the real-time code that is determining whether a safety critical event has occurred, so stop the line, turn the machine off, open up the valve, blow off steam, that stuff should remain at this level of the stack because it has to be instant. So a lot of, to address your concern about safety, is the right architecture. Certain workloads should happen where they currently are. Other workloads can and should happen in more modern technologies like cloud computing. And in fact, IoT in general, particularly industrial IoT, is a very hybrid architecture. There's stuff happening from the edge to the cloud and everywhere in between. But this is something that we are extremely mindful of, as are our customers. And I need to be more mindful of that power strip. Oh, good. Yeah, thank you. The question was safety. So I'm going to work fast because I'm getting low on my time. Verbose. So here's a different use case. The last few use cases were a product that was being serviced, and we wanted to know how to service that product better. Here's an example of a manufacturing operation. And this use case was they're stamping out automotive parts. And you stamp parts with a die. And you can only use the die so many times before it fractures and fails. Well, the automotive manufacturer is on the other side of town. This factory is stamping out the parts. They go right on a truck and get put into production immediately, just-in-time manufacturing. Has to be very precise. You can't have a die crack during a production run. Just can't let it happen. So what do? You replace the dies very aggressively. Probably far more often than you have to. Replacing a die is expensive, it has to be done off hours, it costs money, etc. So we'd really like to know, in a more smart way, what is the usable life of this die right here? So this is an example of applying machine learning technology. The humans don't know how many cycles it can go, how the humidity and temperature and operating conditions affect that die's life cycle. We're going to learn with machine learning. But here's an example of where the technology is there, but sometimes the customers aren't. And I'm not speaking specifically about HeroTech. They're a fantastic customer, a fantastic institution. But if I want to know, how can I predict a future event? Failure event, I want to predict. I need historical data. What I told you a little while ago about machine learning, it doesn't know anything. It looks at values and it sets numerical weights. So if you want machine learning to predict a failure, you have to show it what a failure looks like. You have to show it this happened, and this happened, and this happened, and this happened. I don't know if all this stuff is related, but all these things happened, and then a failure happened. It cracked. So if a manufacturer has not been capturing these events, they're not going to get machine learning this month. Right? So a lot of what we do is help them on a path to capture clean signals so that you can get to predictive learning. And along the way, some things we can do is detect anomalies. We don't know what all the events and their outcome events look like yet. We're capturing historical data. We're going to train machine learning models. We're going to get there. In the meantime, it doesn't take long to start using the same technology to say, something looks weird. We don't know if it's going to be a problem, but this is not what normal looks like. And again, if the human operators already know what normal doesn't look like, that's great. But sometimes the machine learning can find very surprising results. We're the same there. Here's an example, cornflakes, potato chips, process manufacturing. In process manufacturing, by the way, has historically been, or is, the last 20 years, much more automated than discrete manufacturing. So in discrete manufacturing, I've got a little work cell. We're working on some stuff. We got some machines. We're making a part. Part gets put on a bin. Somebody wheels it over to the next part of the work cell. And that's how products come together. It's not all like the how it's made things where you have this vision in your mind that it's automated from end to end, and then something spits out an iPad at the end. It doesn't work like that. Right? Parts are automated, but the final assemblies are usually manual. In process manufacturing, a cornflake does get automated. Potatoes in, potato chip. That'd be pretty wild if you had potatoes in and cornflakes out. Wow. So despite the prevalence of automation in process manufacturing, food and beverage, they still didn't have this connection between their systems. So this is really an IT problem, right? It was an IT problem of how do I take information here, information there, and put it behind a single pane of glass so that the people who are making the decisions, the plant managers, have everything they need in one spot. And a lot of what we do is just that IT system and OT system, operational technology, aggregation. Okay, so now we get to the people. Here it is. By 2025, 2 million manufacturing jobs will go unfilled. So does that mean that automation is not displacing workers? No, it is, certain kinds of workers. But on the other end of the continuum, there is the demand for highly skilled workers, someone who can do complex assemblies that cannot be automated. And those workers need to understand technology. They need to work with technology. So augmented reality is very interesting to help with this problem. With and by the way, augmented reality is, you may have heard of Pokemon Go. Here's how to think about augmented reality. When you've all heard of VR, virtual reality, that's when the whole world is rendered in a cartoon-like, computer-generated 100%, playing a video game with a VR headset, if you've ever seen those. They make you sick. Why do they make you sick? Because the whole world is generated. With augmented reality, the base scene is reality. It's a camera view, or your real eyes seeing the base scene, and digital artifacts are being superimposed on reality. So in the real world, you're doing real world activities, not playing a video game, and the augmented reality helps you do your real world job like you have superpowers, like you're RoboCop. And a couple of enabling technologies that let us finally do this at scale are computer vision. Computer vision, which is, by the way, a kind of artificial intelligence. With computer vision, we can now snap onto a real-world object and track it. When I snap onto this chair, the computer vision can watch where the chair is, or as I move around the chair, where it still is. And the computer vision can map out my space. It can know where I'm at. There's a floor there are walls there, the chair's there. Okay, so now how does that apply to a real-world use case? Play. Okay, Howden again. This is the air movers and gas mover people. So this is a Microsoft HoloLens this guy's strapping on. He's using a PTC product called Vuforia Studio to drag and drop a VR, AR experience. And now in front of, try to pause there. Get back to the cool stuff. Yeah, we don't need to see. There we go. So now he's in front of the machine. This is an air blower. It's a blower. In the old days, he would have had to walk around to the other side and look at a crappy little HMI panel that showed maybe a few controls about what's going on with this machine. Now he can be anywhere spatially around the machine and see at a glance everything he needs to know about this operation. And by the way, if he has a repair, and you'll see a lot more of these demos at the 4 o'clock keynote presentation with my boss, Jim Heppelman, and Michael Porter. But imagine, so here's a repair operation. 20 years ago, we printed out instructions. And if you ever did work on your cars yourself or anything at home, you had the instructions, and the drawings were always crappy, and you can never really tell by the drawing what you were actually looking at. Stuff in the real world is grimy, greasy, dirty. Even with YouTube videos, you still don't have this perfect match. We can't afford to have that in the industrial world. We need technicians like this guy to get up to speed immediately. I can't have you following somebody around for 6 months before you can do this repair operation, no matter how complex it is. So we believe that the combination of IoT for sensing what the machine is doing and augmented reality to give humans the benefit of that sense in real time is quite a magical combination. So here's another shameless plug for the 4 p.m. keynote here. That's my boss, Jim, over here, and that's Michael Porter over there. He's from some other school around here. Pretty smart guy. So that's digital transformation in a nutshell. Products optimizing how they can perform their job better, how we can make the processes that use those products or produce those products more efficient, and how can we arm our new next generation of workers with superpowers so that they can make sense of all this stuff. So next month, actually just a couple of weeks, PTC has our annual conference. It's really an industry conference. It'll be right here in Boston at the BCEC. 6,500 plus technologists. Wow, stop right there. 6,500 technologists. That's a joke. It's nice that they're all there, though. But breakout sessions, learning about technology, obviously learning about PTC products, but also hobnobbing with other customers that are doing this stuff and our partners that are helping them do that stuff.